I've mentioned more than once that elimination reactions are more likely to happen if you heat them up. In other words, heat tends to bias the reactions toward elimination. And you may be wondering why that is the case. And there's really two good answers for it, and one fundamentally comes down to entropy, and the other comes down to Chatelier, where you can drive off some products. So what do I mean by entropy? Well, if you have taken Chem 120 or Chem 190, or you are currently in Chem 120, then you've probably seen this expression already. If not, then you're about to. And this is the Gibbs free energy expression. Gibbs free energy, a large negative number, essentially means that the reaction is likely to take place. And it's really made up of two different terms. One is enthalpy, which is essentially a measure, in my mind, of how much bond energy there is in the system. So you can take this molecule here and figure out what all the bond energies are and sum them all up. And then you can figure out what all the products are that you've made and sum those energies up. And in the end, you'll find out that there is either some likelihood that you have improved things, that your energy has gone downhill, you've generated some energy along the way, or that it has cost you energy. You have to pump energy into the system in order to make this happen. A large negative one, in other words, that the products are lower energy than you started, will then lead to a more favorable process. It's more likely to happen. So that's kind of the main term. Bond energy is the enthalpy part. But there's also an entropy term, and that comes down to essentially randomness. And the greater the randomness of the universe, the more likelihood that the reaction will take place. And so the main idea to think of here is that small molecules are likely, generation of many small molecules is likely to lead to higher entropy than not. And so your larger steady molecule here generates a couple of smaller molecules in the products, and that's usually what's happening in an elimination reaction. If nothing else, what we have done is generate, say, HCl, which will then be floating around in solution, or if we're heating it up enough, could in fact boil off. And the idea behind Le Chatelier is that you can remove products from a system and cause it to go further, shift equilibrium in the direction of products if you are pulling products out of the system. And so small molecules that have a tendency to evaporate off, especially if you're boiling the reaction mixture or just plain heating it, those are things that are going to bias you toward elimination, both because there's more entropy involved and because you're actually potentially removing some of those products by evaporating them off. But the other thing I want to point out here is that you have this term right here, which depends on temperature. So the entropy is a function of the temperature. And so the higher the temperature of the system, the more important this factor becomes relative to the bond energies. And again, whenever you're doing an elimination, by definition, you're creating at least one new small molecule in there somewhere because you're eliminating it. And so the higher the temperature, the more likely this term is to dominate, and it makes this process more spontaneous. The elimination process becomes more spontaneous as you heat it up. So if you would like to bias things in the direction of elimination, what you do is you heat it up, because that engages both ideas. You can Le Chatelier, you can pull off the small molecule products that you are forming, and or you can also just take advantage of that temperature term and make the entropy a bigger consideration. Over here, what I have is a setup that Professor Pelkey describes several different times. Whenever he's talking about a Dean Stark trap, what he's talking about is a piece of glassware, and what it looks like in action is this. And so what you have is a round bottom flask, and you have a heat source. Normally we don't use Bunsen burners because we don't actually want to catch the lab on fire, but a heat source down here, and so you're heating this up and it's boiling, and what happens as you go is you start distilling this mixture. So this starts coming up, and then right here we have a condenser with cold water running through it, and this area right here starts to fill up. And so right now what I have in there is a mixture of a couple of solvents, because typically what you will do in a Dean Stark trap is use either benzene or toluene as your main solvent, because what you're explicitly trying to do is remove the water. And so if there's a small amount of water present, so now let's imagine that we've changed this so that what we're doing is eliminating an alcohol. So we're generating water as part of the reaction. So we're generating water, and it's now one of the main byproducts of the reaction. And so this blue is the water that's in my benzene, and this yellowish solution is the benzene itself. What happens is down here you have both benzene and water, but as you heat them up, they come up here and condense, and then the water starts condensing out, and then benzene is less dense than water, so it will flow back down into your pot, so you keep recycling. And over time, what happens is that the amount of water present originally fades, and you end up filling up this container with water right there. And so what you can basically do is, again, force all the water out of the system to collect up there, whereas the benzene will come back down, and then you keep reheating. And again, what you're doing is you're making the water go away. And this is, again, a way of doing Le Chatelier. You're pulling this product out of the system by trapping it in a different location, and that will shift the equilibrium towards, again, the elimination products. So if you see Dean Stark, what that means is you are explicitly removing water. It's a benzene setup where you're heating it, and what it's doing is pulling water out. And if you're pulling water out, I just about guarantee that what you're trying to do is some kind of elimination of an alcohol. And in the Dean Stark case, you're both exploiting the entropy idea and the temperature idea, and explicitly the Le Chatelier idea of removing removing one of the products from the system and causing equilibrium to shift in that direction.